Here, Sam Harney wants to say hello. Oh, wait, no, you have to say hello through here. Scream it out.
Guten Tag.
Wow, that I didn't expect that. That was kind of fun. Yeah, yeah. Bye. Okay, so I want to take us from the end of the class where you guys were having trouble distinguishing between left and right and explain the second part of this concept here, the part that I'm circling here in green. Okay? Because I didn't have a full enough time to be able to answer that. So let's discuss this. So again, let me just make sure you understand what's happening. If you take a look at the periodic table, and let's say we had scandium, which is atomic number 21. So I'm just going to go ahead and write in 21 right here. Boy, this is way too fat. Hold on, I got to trim down my point. How do I make it skinnier? How do I make this skinnier? Oh, there we go. All right. All right, here we go. Here we go. I got it. And now I'm going to erase this. There we go. All right, so this is atomic number 21. And right next to it, we have atomic number 22, 23, 24, etc. Okay. So if you were to imagine that you had an atom, how come this is a gray background? Is it always gray? Strange. Imagine that I have an atom that has 21 protons hanging out inside of it. So I'm going to have, positive, positive. Make this a positive. Okay, 21 of these positive fellas. And then I have, if I were to compare it to an atom that instead of having 21, instead has, say, 24 protons hanging out in here. Now, if you were to take a look at it in terms of the effective nuclear charge associated with this one, I hope you all understand that this guy right here has a higher effective nuclear charge as compared to this dude right here, right? This one is a high effective nuclear charge, this one has a lower. And again, the whole point of the concept of effective nuclear charge is that it's the attractive power that the nucleus can exert on the electrons that are cruising around it. Okay? So if I have a high effective nuclear charge with this guy right here, that means it's going to pull its electrons closer to it because it has more power to pull those electrons closer to it. Now, of course, we increase the number of electrons, right? But as you increase the number of electrons, you actually haven't increased the principal quantum number. So you haven't added layers, you've just added electrons. In other words, it's like you, if you're equating it to the metaphor that I used before about putting on layers of clothing, it's as if you put on a sweater, but rather than adding anything above that sweater, maybe you just simply added a couple more threads, or it's not threads, yarn, a couple more lines of yarn to it. It's not really going to change overall a significant amount of the bulk of that sweater if you add a few more lines of yarn. Not unlike, it would be very different if you decided to add an entire down jacket over top, because that certainly adds a whole nother layer to the whole thing. All right, so as a result of having the stronger effective nuclear charge associated with this dude and its ability then to draw electrons closer to it, even if you have more electrons, since you haven't changed the principal quantum number, all those electrons are pulled a little bit closer to the nucleus than the atom that is atomic number 21. Okay, so the atomic number 21 has a weaker pull on the electrons because it has a lower effective nuclear charge. So again, let's go up to here. Looking at this, if we have a relatively high effective nuclear charge and a relatively low effective nuclear charge over here, then you can imagine that we'd be going from having something that is going to hold its electrons tightly to something that's a little bit bigger, to something that's even a little bit bigger than that, to something that has the lowest effective nuclear charge, and therefore the electrons can cruise around further away from the nucleus. Okay? And if we cruise back to where we actually wrote this, that's exactly the trend that's followed over here. You have the smaller radius associated with the atom that's further over to the right side of the periodic table. All right, so that's atomic radius. Oh, hold on. There's a distracting teacher here, Bogosian, trying to mess with me. All right, so let's take the let's look at the next periodic trend, which is in fact follows the exact same concept as what we were just talking about in terms of the trend, and that is ionic size. So before we can do that, however, I need you to add another empty periodic table to your notability document that already you've created that had the atomic radius in here today. So you might need to pause a moment and get that in there. And in the meantime, I'm going to go ahead and put up an empty periodic table too. All right, so I trust that you got this empty periodic table stuck into the notes that we were taking on notability. And we're going to be talking about something called ionic size. And before I can actually do that, let me unlock here for a moment. I need to explain the concept of an ion, which I think most of you understand at this point. So imagine we have a neutral atom of calcium, and if I were to find the most common ion form, I would discover that calcium likes to be Ca plus 2 or 2 plus, which means that if calcium has an atomic number of 20, in order for it to be a positively charged ion, that means it will have lost 2 of its electrons, right? So it would still have 20 protons, but it would only have 18 electrons. So when you combine the 20 protons and the 18 electrons together, that's what's going to give you the plus 2 charge associated with the calcium. Okay, so that's the concept there. I'm just going to erase this crapola off to the side. You don't really need that hanging out there. And so when we talk about, you know what, ionic size, I wrote this, it's too fat. I need to make this thinner. How can I do? Well, I don't know if I can. I guess that's it. I can't do any better than that. Darn it. Anyway, so ionic size. Now, before we can do ionic size, it's important for me to run through and give you some semblance of the most common ion associated with the particular groups. So over here on the block that contains hydrogen, oh boy, I'm going to do plus 1 here. You know what? I think I'm going to try to import another periodic table because I can't get this one to be any bigger than right like this, and that's a stinker. So hold on just a second. All right. Not sure this is going to work, but we'll see. So, oh yes, it's better. Ionic size. Okay, now I can go over here and start labeling these things a little bit better. So all the, in the alkali metals here, they're all going to be plus 1s. The alkaline earth metals are all going to want to be plus 2s. Then I'm going to jump way over here. And the group 3A, these are going to be plus 3s. And actually, I should say the non-metals will be plus 3s. Sometimes the metals get a little messy. And then we have plus 4 in group 4A, minus 3 in 5A, minus 2 in 6A, minus 1. And then the noble gases, they don't they don't make ions, so we leave it at that. But this is going to be an important thing to understand, because if we look at the size of the most common ion associated with these particular atoms, all right, so now I'm going to draw a down arrow indicating that the ionic size, the size of the ion, increases as you move down in a group. Okay? And similar, that's the exact same thing that we saw with these guys, right? It increased in size as you move down for atomic radius. Okay? So with ionic size, it does the same thing, and in fact, the same trend exists, although I'm not going to bother starting with the noble gases since they don't make ions. I'm going to draw a line going to right here in red. Now this is important. I made that one in red because then I'm going to change the next arrow. I'm going to make that one green all the way going across. And just like you guys hated this whole sort of reading things from right to left, I'm going to do the same thing going on here, which is that ionic size increases going from the right side to the left side. Okay? You'll understand in a moment why I broke the arrow into two, a red one and a green one. But for now, just have it as that. So the reason why this is the case, it's going to make a whole lot of sense as we move forward. So let me, actually, let's go ahead and write things in here for a moment. So I'm going to write here that ionic size increases in this direction. I'm not even going to bother saying from right to left. Okay, ionic size increases. And then I could do the same thing over here. Ionic size increases going in this direction. Okay? Oh, hold on. So, you guys, it's fun because I'm here talking to another teacher who's wondering how I do this. And so remember, Cece, when you see this, you'll see me expanding it, contracting it when I'm talking to you in the thing when I send you the link. Okay? Okay. It's fun. It's totally fun. You'll love it. All right. So where was I, you knuckleheads? Oh, yeah. I was basically trying to tell you that ionic size is going to be the same trend that we saw with atomic size. Okay? But there are some subtle differences that are important here. Let me go ahead, however, and put in some things here to show you. Remember how we showed yesterday or today in class how the things get bigger? Now, I wish I could make it opaque. I bet you I can. Oh, yes. Yes, watch. You guys are going to love this. Okay, so I start off a little bit small, right? And then it gets bigger, 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 biggest. All right, and then we're going to do the same thing over here. We're going to start off with something small, a little bit bigger. Right? Looks like crayon, doesn't it? And if we're going in the other direction, so if we're going across a period, backwards across a period from right to left, we're also going to see the increase. So I get bigger here, but I'm going to stop there. So notice that it definitely got bigger from my 7A element to my 6A element to my 5A element. But suddenly when I jump into my 4A element, and I'm going to change the color here too, to red, I go wee itty bitty again. But then from that point, I get bigger. So, and I'm going to jump across, all right? And this too is, oh, I guess I should make this one green. Let's see how that increases. It's going to increase in size from the 2A group to the 1A group. Okay? So again, it's following the exact same trend that we saw with the atomic size, except that we have this wackiness going on between the group 5A and group 4A. In fact, maybe I should write that in there. So, okay, so we go from 5A here to 4a, we see some funny little inflection. And the reason for that is exactly what you can imagine having happened here. We go from being a most common ion form of -3 to suddenly being the most common ion form being a +4. Okay? So let me pause for a moment. Okay, so I want you to think about this. When an atom becomes a positively charged species, so it becomes a cation, that's what an ion that forms a positive charge is called a cation, it loses an electron, right? And when it loses an electron, you also reduce the repulsive forces of all the other from the electron being lost, right? Because the electron adds some level, it might be small, but it's still going to add some level of repulsive force. And so all the other electrons then don't feel as repulsed from each other as they did when that electron was there. So now when you remove that electron, then all those electrons actually can get pulled closer to the nucleus, right? So when a cation loses an electron, you reduce the overall repulsive forces. From all the other electrons, right? And as a result of this, you can, all the electrons can be pulled closer to the nucleus. And that's why you can see that if you're just taking it from the perspective of a positive or a negative electron, it's going to change. So let's go back here. In this case, a +4, right? If we look right here, the +4, that's lost 4 electrons. So that's losing a significant chunk of repulsive force, as opposed to just the opposite that we have going on right here, where you've actually added electrons to this whole thing. And if you add electrons, then they're all going to be repulsed by each other more, and they're going to be wanting to be further away from each other. All right? Okay. Now, the other thing that you should understand here is that these most common ion forms, right, the +1, +2, +3, +4, etc., they are the result of electrons vacating their valence shell. And if you have electrons that completely lose a valence shell, that means you've just essentially shrunk yourself by that valence shell. So if we go back to what I was talking about earlier, in a sense it's like taking off your down jacket. You lose a layer and you get skinnier. All right? So the fact that these cations lose electrons, that means they vacate, oops, got to go to this, vacate their largest orbital, whatever that orbital was, the valence shell orbital, or sublevel, I guess I should call it too. All right? So the combination of those two things, reducing the repulsive forces and vacating your largest orbital, is really going to make this thing shrink tremendously. All right? Now, let's take it from the perspective of an anion. So if we have a negatively charged, I really should have done, the blue should have been the negative and the red should have been positive, but oh well. Your fault. So when you form this, you form something called an anion. Okay, so a negatively charged ion is called an anion. And when this happens, instead of losing, you gain an electron, right? And as a result of that, instead of reducing repulsive forces, you increase the overall repulsive forces. And if you increase the overall repulsive forces, then guess what happens? All these electrons push away from each other. Oh, you know what? I didn't put electrons. Oops. Let's add. So electrons can be pulled closer. So, all right. So the electrons, boo, push away from each other. That's an O. And if they push away from each other, they expand in size. So the more electrons you lose, right, the more you're going to get this expansion, which explains what's going on here between -1 to -3. You lose more electrons as you go from right to left, and therefore it gets bigger. Okay? Now, how about this part? What explains that? Because these are all going to be the +1, which means they're all going to lose an electron. And they're all going to lose an electron, but keep in mind that if they are all, if we go back to this trend, right, the atomic radius, then we're talking still about these dudes having the extra, they're moving up a principal quantum number, so that means they're just getting bigger for the having more electrons and protons in larger and larger orbitals. Okay? All right. So I hope that explains the concept of ionic size, and tomorrow in class we'll do a couple more periodic trends, and they'll be just as fun. See ya.